Welcome to the lecture of subject signal systems KEC 403, and we will be discussing types of signals in this lecture. How is the formulation of discrete time energy and power signals is done? So the energy content of a discrete time x of n, the integration that was done in continuous time will be replaced by summation in discrete time. So we will use a variable n and we will sum for, or we can also use the limits. So the formulation will be something like this, that this is limit n tends to infinity summation in n starting from minus n to plus n, and we can use mod x n square, and we can evaluate this summation. This summation is finite in nature. We calculate the summation first and then put the limit of capital N tends to infinity, and then analyze whether this is finite or not. If this is finite, the signal is energy. Otherwise, the energy is infinity, and we move to calculate the power. So power content, I discussed earlier also, is the rate of doing work. So to total durations, we divide the expression by total duration. In the last case, for continuous time signals, the duration was from minus capital T to plus capital T. So total duration between minus capital T to plus capital T is 2t. So we divide by 2t. Now, in this case, this is a discrete time case. So we are evaluating from minus n to plus n. You can understand, since it's a discrete time case, the point n is equal to 0, small n is equal to 0 also exists. And for that matter, there are 2n plus 1 points between minus n and plus n, and that needs to be the divisor factor. So what we have is that limit n tends to infinity. In here I will have 2n plus 1, because the total number of points between minus n and plus n is 2n plus 1, and then the same formulation, that n starts from minus n, goes to n mod x of n square, and we evaluate this. If this comes out to be a finite value, the signal is a power signal. In this case also, the periodic signals will always be power signals, that remains. Truncated signals will be energy signals. Signals which are not periodic may be energy, may be power, depending on the mathematical formulation of the signal. This is how we evaluate. Now we look at few cases. Like in this case, it is e raised to the power minus j 2 pi n. So this is a discrete time complex exponential, isn't it? This is a complex exponential due to the presence of j. So if I evaluate the energy content, you can understand it is periodic. The energy content of the signal will be infinity. One can verify, but we will calculate the power content of the signal. The power content of the signal is limit capital N tends to infinity 1 upon 2n plus 1, and the summation is from n starting from minus n to plus n, and mod of this thing square. So it is mod of e raised to the power minus j 2 pi n square. So if I do this, you can understand the mod of complex exponential is 1. We have already discussed this in the previous slide. So we end up getting k square. So it is what? It is, even k is not a function of n. So I can write k square just to make it more clear, and then I will write limit n tends to infinity, the divisor factor of 2n plus 1. Now the summation is n starting from minus n to plus n of 1, because k I have taken outside. So the mathematical formulation that needs to be evaluated is summation of 1 from minus n to plus n times. So we have seen that from minus n to plus n, how many points are there? 2n plus 1 points. So 2n plus 1 times I am adding 1, which means to say the sum value is 2n plus 1. So basically this is k square. The results resonate with what was in continuous time. K square limit n tends to infinity and 1 upon 2n plus 1. The summation also is 2n plus 1. So these both cancel out, and the p infinity, as we expected, is a finite value k square. Signal is a power signal since it is a periodic signal in discrete time domain. In discrete time domain, the signal is periodic. One caution one can take, even if this pi part is not present, the signal becomes aperiodic due to absence of pi. In discrete time, complex exponential sines and cos are not compulsory to be periodic. So if there is no pi, the signal will not be periodic, but since it is complex exponential, the modulus of it will still remain to be 1, and therefore it will also come to be power. So it is not necessary that if the signal is aperiodic, it cannot be a power signal. Signal can be a power signal. So in complex exponential, sine and causes, in all the three cases, we can also verify that. Now there is a signal, suppose un minus u of n minus 1. So this is a case, sure case of signal being finite. What does this signal look like? This signal look like starting at 0, 1, here it is at minus 1, it is 0, and it goes to 5. The signal is this xn. So by mathematical formulation, it is limit n tends to infinity minus n to plus n mod xn square. We put the values of the signal. The signal is basically 1 from 0 to 5. The points of 6 and above will be discarded. So what it is actually, the signal is 1 between other formulations are also written, but it is from 0 to 5, it is 1. So what does the summation will look like? It is addition of this in 5 times. So basically you can understand that the energy content of the signal is 0 to 5, 6 times addition of 1. So it is 6. So since 6 is finite value, we get the energy of the signal. The signal is energy signal. Because it is a truncated signal, the signal is was supposed to be an energy signal. It is an energy signal. If the signal is energy signal, the power content of the signal is infinity. By mathematical formulation also, P infinity is limit n tends to infinity 1 upon 2n plus 1, and what we evaluated, the 6. So it is 6 by 2n plus 1, where n tends to infinity. So basically it is a finite by infinity, which gives me 0. So this truncated version of xn is an energy signal. I was using this statement that truncated signal are also energy signals. So this has been proved here. Cos is, you can understand, cos 2 cos pi by 4 n is also a periodic signal in discrete time, and therefore it will be a power signal, and the same is c square by 2 is the result, and therefore the value that we'll get is 2a square by 2, which is 2. The answer is 2, which we can see from this expression. Third is similar to what we use TUT. So this is NUN, and here if we evaluate both the entities, in this case first of all it is UN and n square, so it will become n square and n square summation from 0 to n, and n tends to infinity. So we are adding n square n plus 1 times, and then this means what? This means that this is limit n tends to infinity, and what is this summation? This is n square into from 0 to n, n plus 1 times, and then I put this limit of infinity. So this is basically infinity. The energy is infinity. Even this expression is divided by 2n plus 1 in power, in the formulation of power. It is not possible for this to be a finite power signal, and therefore the signal is neither energy nor power. Another category in which we divide signals is of even and odd functions. A signal is said to be even, and arbitrary g of t is said to be even signal if g of t is equal to g of minus t. So there is a symmetry by ordinate axis. The ordinate axis, with respect to the ordinate axis, we have a similarity, which means that what is g of minus t is equal to g of t. So in y axis there is, about y axis there is a symmetry. A signal is said to be an odd function or odd signal if g of t is equal to minus of g of minus t. So in this case you can see that the symmetry, or it is actually anti-symmetry about the origin. So the first and the third quadrant, or the second or the fourth quadrant, will look opposite in nature. This is what odd signal looks like. If there is any signal g of t, we can find the even part of the signal by this formulation. The even part of the function gt can be evaluated by calculating gt plus g of minus t by 2. Similarly, the odd part will be subtraction. So it is g naught of t is equal to gt minus g of minus t by 2. If we do this, we can represent even and odd part of any arbitrary signal. Let us perform one quick example to illustrate how this is done. So suppose we have a signal x of t is equal to k e raised to the power minus at ut, and we want a formulation of even and odd components. You can see x of t is basically the same signal. X of minus t, we put u of minus t. So u of minus t, by virtue of its definition, u of minus t is 1 for t less than equal to 0. It is 0 for t greater than 0. It is just the reversal of u of t. So for if I use this expression, I will get basically x of t, x of minus t by 2. This is the formulation, and the odd part is x of t and minus x of minus t by 2. So this is straightforward. Now graphically, if we do this, we will also find that there is one more thing to look into, that I have also provided in terms of limit, but graphically it is more clear. Suppose the xt looks like this. The xt is k, so e raised to the power minus at ut. Ut means it starts from 0 and goes to infinity right hand side. At t is equal to 0, if we put, we will get e raised to the power 0, 1 and k. So value at t is equal to 0 is k, and this is in the first quadrant. The signal is in the first quadrant. Now if the second part that needs to be subtracted or added as per the definition is x of minus t. What is x of minus t? Reversal of the signal about y-axis. We are taking the mirror image about the y-axis. So whatever the signal was, it is a mirror image of that. It is decreasing in time still, because the time itself is negative in this case. So in the second quadrant, it is decreasing. Now as per the formulation, we also require minus of x of minus t. So x of minus t was this, the second quadrant. Now if I take minus in the magnitude part, it will be reversal by the abscissa, the x-axis, and therefore the second quadrant signal will go to the third quadrant. The values are very clear. The values in this case here is k, in this case here it is minus k, and in the first case it is k. So now if we perform even an odd component calculation, it is now visually very clear. The even component of the signal is x of t, basically is half of x of t plus x of minus t. This is x of t. This a is x of t. This b is x of minus t. I am adding the 2 points. It is very clear. This is the first quadrant signal. This is second quadrant signal. We will get a symmetrical signal, and it looks like an even signal. So graphically, we are getting an even signal. That is fine. What happens at t is equal to 0? At t is equal to 0, the a has an amplitude of k, the b has an amplitude of k, and the formulation has an half. So at exactly t is equal to 0, we have k plus k by 2, which means the magnitude of the sum signal, the even component of the signal, is bound to be k at t is equal to 0. We just move to the left, that is t 0 minus. At t 0 minus, the component of the b is k. And similarly at t 0 plus, the component of a is k, and the formulation is by half. So what we will get is k by 2 at t 0 minus, at t 0 plus we will get k by 2, at exactly 0, the limiting condition will get exactly k. So this is generally the most important and identifying feature of this question particularly, that there is a discontinuity in description also. This also mathematically one can prove, like here I have proved mathematically by implementing the limits, you can get the same thing, but still we need to, graphically it is more visually clear that at t is equal to 0 the signal is different, at t 0 minus the signal is k by 2, at t 0 plus it is k by 2, and at t is equal to 0 it is k, which means that there is a discontinuity. What happens to the odd part? The odd part is basically the a component and minus the c component. The c component is the reversal of x of minus t, so which is the third quadrant signal. So if we subtract, or we say we add a and c, if this is c and this one is a, then what we are doing, we are adding a and c. This also means that we are subtracting a from b. So if we are doing this in this formulation, you can see a was k at t is equal to 0, and c was minus k at t is equal to 0. So what we are getting, k minus k by 2, which means 0. So at a particular, this t is equal to 0, the signal is 0. At 0 minus, this signal was minus k, and by formulation it will become by 2, so minus k by 2, At t0 plus, it will become plus k by 2. The signal is odd. There is antisymmetry by origin. So by definition, it is antisymmetric. But at origin, there is a distinctive discontinuity. At origin, the signal is 0. And otherwise, the values at 0 minus and 0 plus are minus k by 2 and k by 2 respectively. So this is also a very important feature for this numerical. If one plots, it is easy to visualize that it is not only xt plus x of minus t by 2, but it is also the discontinuities that need to be catered. For discrete time signals also, one can formulate the even and odd parts of the signal. So suppose there is a discrete time sequence, it is called a sequence. So if it is sequence, we always use n is equal to 0 pivot point to represent what is n is equal to 0. This means that at the right of it, there are n is equal to 1 and n is equal to 2. To the left of it, there is n is equal to minus 1 and n is equal to minus 2. So if I want to plot the even and odd component of this signal, the formulation of xe of n is basically half of x of n and plus half of x of minus n. So what we need? We need x of minus n basically. So what will be x of minus n? X of minus n will be just pivoting the point at n is equal to 0. What is n1 will become n minus 1. What is n2 will become n minus 2. What is n minus 2 will become n2. What is n minus 1 will become n1. 0 remains the same. That is the pivot point. So it is basically mirror image about the y-axis, similar to the continuous time case, but just the time indices in this case is integers, and we'll get this. Okay, so we'll get x of minus n. So now if we use this formulation, it is very straightforward. Point by point addition of this and this is to be done. So what is xe of n? The half remains. So half also we can write there. So it is minus 3 and plus 2. It becomes minus 1 by 2. Then this is 1 and minus 4, minus 3 by 2. And 2 and 2 will give me 2 by 2. Minus 4 and 1 will give me minus 3 by 2. We don't even need to calculate further. It is an even signal. It will be a mirror image about n is equal to 0. It will be minus 1 by 2. The signal has to look like a even signal after calculation by the property of it. What will be the odd component? The odd x naught of n by definition is half x of n minus x of minus n. So in this case, what we need to do, we need to subtract this from this. So what will be this if we do that? The first signal is minus 3 at n is equal to minus 2, and this signal is 2. So it will become minus 3 minus 2, which is minus 5 by 2. Then we move at n is equal to minus 1. At n is equal to minus 1, the signal is 1 and this signal is minus 4. We subtract, we get 5. So we get 5 by 2. By default, the origin has to be 0. There is a odd antisymmetry about the origin, but you can also calculate 2 minus 2 will give you 0. So 0, and this is the n is equal to 0 point. Then we move to the right at n is equal to 1. The first signal is minus 4, the second signal is 1. So it will be minus 4 minus 1 by 2. So we will get what? Minus 5 by 2, and therefore the final signal will be also opposite in sign of this and will be 5 by 2. And therefore what we get is an odd antisymmetric signal. So this is all about how we evaluate various types of signals, whether the signal is a periodic signal or a aperiodic signal, or a signal is a energy signal or a power signal, or the even and odd components of the signals. Continuing with the example of breaking a signal in even and odd components, sometimes we can also not refer to only as graphical methods, but the analytical expressions can be used to find even and odd components. Suppose we have a signal xt is equal to e raised to the power j 2t. Now this signal is of course continuous in time, and due to the presence of this j component, the signal is complex. So signal is complex exponential. The definition for complex exponential by Euler's theorem is that e raised to the power j theta is cos theta and plus j sin theta. And if we take complex conjugate of it and add and subtract, we can represent both cos and sin using the equations e raised to the power j theta plus e raised to the power minus j theta by 2, and sin theta is e raised to the power j theta minus e raised to the power minus j theta upon 2j. So in this manner, we can use these properties to find the even and odd components. What is the definition for even component? Suppose xe of t is actually the even component of the signal x of t. So how it is defined? Xe of t is defined as x of t plus x of minus t upon 2. Now looking at the definition of x of t, we can just substitute here. This then becomes e raised to the power j to t plus e raised to the power minus j to t by 2. So this is the even component of the signal e raised to the power j to t. If we compare this with this, cos theta is equal to e raised to the power j theta plus e raised to the power minus j theta by 2, then we will be able to write this as even component of xt, which was given is basically cos of 2t. So the even component of the signal xt is equal to e raised to the power j to t is cos 2t. We know that cos 2t is an even signal. The cos is an even signal. By definition also, it should be even, and since it is cos, due to its basic properties, it is bound to be an even signal. So even part of this signal is an even signal. We can also formulate for the odd part. So x naught of t, which will be odd part of xt, will be defined as x of t minus x of minus t upon 2. So if we use this definition and substitute the value of xt, we will get the odd component of xt as e raised to the power j to t minus e raised to the power minus j to t upon 2. But we know that in the previous slide I have defined, and I am again defining, that sin theta is e raised to the power j theta minus e raised to the power minus j theta upon 2j. So if I compare this with this, you can understand there is a missing j element here. So what we need to do, we need to introduce the parameter j in the denominator. We cannot do it by ourselves. It is a phase component, so we will also need to multiply by the same amount in the numerator. If we do that, now this becomes a sine, and therefore the odd component of e raised to the power j to t is j times of sine 2 t. Sine by its property is an odd function, so basically the odd component of the signal is an odd function. So in this manner we can differentiate various kind of signals. The signal can be energy power, the signal can be periodic aperiodic, the signal can be even and odd, and in even and odd we can have sequences, discrete time sequences, we can have discrete time systems, discrete time signals, we can have continuous time signals, and continuous time signals and discrete time signals can be evaluated in graphical method, or they can be calculated directly using the analytical expressions by the definitions. So this is all about this lecture. Thank you.